Hi, in this video, we're going to get into the basics of cross products. And I've identified the things that we're going to look at in this video. The first thing is vector notation. Some of you may already know this stuff, but some of you might not. So I want to make sure we're all talking about the same things. The second thing is treating cross products as areas. So we'll talk about areas then as vectors, which might seem a little bit strange, but hopefully I'll be able to clarify that for you. And then we'll get into right-handed coordinate systems. So the only cross product we're going to do in this is really, really simple. We'll save the more complex stuff for a future video. So first thing, vectors, vector notations. So the first thing we're going to do is look at vector notations. I've gotten two vectors here, A and B, and I've written them out in two different ways. So the first way is using brackets, but not normal brackets or parentheses. These are little spiky, carroty looking brackets. And that signifies that it's a vector. If I use parentheses like this, right, that would signify a point in space, but that's not what I want. This signifies a vector from the origin to that point in space. I could also write it like this. Okay, this is unit vector notation, and I'll talk about that in just a moment. And this is what this vector looks like. It points 5 to the right. And B is very similar. It just points 3 up in this case, okay? So I've written it out in this particular way. I apologize if you see something flapping down. I'm trying to stop a glare, but it's not super effective. So let's talk about unit vector notation. Hopefully you know what unit vector notation is. If you don't, then I'll try to clarify that for you as quickly as I can. So I hat is really just 1 in X direction, right? And J hat is equal to 1 in Y direction, and K hat is 1 in the Z direction. So all that they are is they're vectors, right? So this one might be like this one might be like that, this one might be like this, kind of coming out of the screen at us, depending on the coordinate system I use. We're going to talk about those in a moment. But they're just one big, but they point in a direction. So if I multiply 5, which is just a scalar, by a unit vector I hat, then what I'm saying is that I'm going to take this I hat of 1 and multiply by 5, so it's going to be 5 times as big. That's unit vector notation, very useful and very important to us as we move forward. So that's all that I've written here. Now, what I want to do is I want to find the cross product. So what does the cross product actually tell us? So the first thing that we can hopefully recognize with the cross product is that it's going to give us an area. That's really what we're getting. And this makes a whole lot of sense if, but only if, it's 2 length vectors, right? So we're used to getting areas from 2 length vectors. If we have something that's not a length vector, then it can be kind of confusing to think of it as an area. But that's ultimately what we're going to be finding. We're going to be taking these 2 vectors, whatever they happen to represent. So it could be a length and a force, which if we take the cross product gives us the torque. But what it's doing is it's giving us the area of the parallelogram that those 2 vectors form. And we have to add them head to tail. So I started with A and then I went to B. So A, B, right? And my area then is just the area here, okay? So that's the first thing. I can find that area, not so hard. It has a value of 15, right? Let me do this in blue. So this has a value of 15. 5 times 3. But you may have heard that order of multiplication matters when we're doing cross products. So I have B cross A. Let's just take a quick look at that. So if I do B cross A, it's going to look pretty much this. If I can actually draw a straight line, it's going to look pretty much the same. Right, but you can see that the order of it's a little bit different, but the size of it is still going to be 15. Now, first of all, let's talk about these areas being vectors, because they are. How can an area be a vector? It's not something that we normally think of as a vector. So what I want you to imagine is, let's say that it's a rainy day and you don't have an umbrella, but you do have a piece of paper. So you get your piece of paper and you want to use this piece of paper to help stop the rain from hitting you. Well, if you orient the piece of paper like this, then it's going to stop the rain from hitting your head. If on the other hand you orient the paper like this, it's not going to stop the rain from hitting your head, assuming that the rain is coming pretty much straight down. So the orientation of the paper matters. And it has the same area no matter what. So it has the same potential to block a swath of rain, right? But if I orient it so that the area surface is facing up, I can block rain. If I orient it so that the area surface is facing forward, then I can't really block the rain. So area has a direction. Now, the other thing that I'm going to try to convince you of is that not only does it have a direction along an axis, right, but it has a direction, say, in the positive of that axis or the negative of that axis. So this might seem strange, but I've got writing on this side, I don't have writing on this side. So I can have it so that the writing side is facing up, or I can have it flipped so that the writing side is facing down. So that's one way to think of it. You know, you could have an area that actually has a different, that has different something on one side versus the other side. Another way to think of it, and probably the more useful way, especially if we're talking about electric fields and that type of thing, is you could think of maybe a container, a barrel, and the top of that barrel has an area. And then you put it out in this rain that we've been talking about, and rain can go into it. Or you can flip over the barrel and dump the rain out, right? So rain comes out of it. And what we use the direction of area for, from these cross products, for example, is to tell us whether stuff is going in or going out. Okay, and you're probably most familiar with cross products related to torque, right? Where we have an R and an F. And you could think of it almost like the same way. Like if you take a screw and you apply a torque one way on it, the screw goes in. If you apply a torque the other way, the screw comes out. So this in and out, area in, area out, is stuff going into the area, is stuff coming out of the area, is a really important conceptual way to understand what's taking place. Now, back to this. When I'm looking at these two things, I get the same area. The question is, which way is the area facing? I understand that because the surface is sort of flat on the screen, that the area vector is going to be either in or out of the screen, right? It's facing the screen direction. So is it in or is it out? How can we tell? We use something called the right-hand rule. Right-hand rule. Now, we only use the right-hand rule because we're assuming that we have a right-handed coordinate system. I'm going to get into that in a moment, just so that you're 100% sure on what coordinate systems we're going to be using moving forward. But I do want to just take a moment to talk about the right-hand rule. There is a limitation that I have. If I do the right-hand rule, for example, so I'm going to do the top right-hand rule here. I put my hand facing the right, curl my fingers up, and then my thumb faces out of the screen. So that's the area vector direction here, is facing out of the screen. And we would denote that with a, wait a second here, I lost my cursor. We would denote that with out of the screen looking like this, okay? And that might be the positive k hat direction, just for example. Now, the problem that we're going to run into in this video and other videos is that I can't mirror my hand. So my hand is, to you, it's going to look like it's going in the wrong direction. So what I have done instead is I've painstakingly developed lots of images of right-hand rules in all the different possible positions, which there's a lot. And I'm going to copy and paste those onto the screen. Okay, so I've got these very sophisticated images, and if you forget how this works, you put your hand in the direction of the first vector, you curl your fingers so that they're pointing in the direction of the second vector, and your thumb points in the direction of the resultant vector. And I did the same thing with B cross A, but of course that changes the hand orientation so that the hand is up, then fingers curl to the right, and the thumb points into the screen. So we have an into the screen direction for this one. And that would look like this, for example. And it could then lead this to be in the negative k hat direction because it's pointing the opposite way. So I can draw the vectors like this, or I could draw them more slanted at an angle like you see with the thumb here. Now, this is the only way that we determine direction is by using the right-hand rule. It's arbitrary, right? Like you could understand that this is into the screen and this the other one is out of the screen. That would be valid too if we used that type of a rule. But this arbitrary rule, the right-hand rule, is what we use to determine the direction for everything moving forward with vectors and cross products, okay? And I just want you to 100% understand that it is the result of an arbitrary rule that we do it this way. Now, it's not 100% arbitrary because it's based on the coordinate systems we use. If we're using right-handed coordinate systems, we have to use the right-handed rule. If we made left-handed coordinate systems, we would use the left-handed rule in order to determine these things. So let me just make sure that you understand what right-handed coordinate systems might look like. Okay, two examples of right-handed coordinate systems are these ones here, where I've got X sort of left to right, Y vertical, and Z is coming out of the screen at us. And the other one, which is the one that I actually am going to be using more often, is this formulation where we've got Y is left and right, Z is vertical, and X is out of the screen towards us. Now, how do we know that these are right-handed coordinate systems? So what I'm going to do is I'm going to walk you through how this works, and I'm going to be using some images of right hands in different positions as we go through this. And I guess just to clarify, you do have to use your right hand for this. All right, so the first example that I'm going to do is, what if we do X cross Y? Well, if we do X cross Y, what we're going to get is a positive Z direction out. And let's look at the right-hand rule example of that. All right, and there it is, where you can see if I've got my hand going into the X, curl it into the Y, my thumb sticks out in the positive Z direction. Now I can also do Y cross Z, and if I do Y cross Z, so Y cross Z, that's going to give me an X direction resultant vector, which you can see here. So you just put your hand up, curl it into the Z direction, coming out of the screen towards you, and then your thumb will point off to the right. Don't look at my hand, look at the hand on the screen and do it yourself. That's the best way to learn how this works. Now, for the last one that we're going to do, we're going to take a look at going from Z to X. So if I cross a Z vector with an X vector, I then will get a Y vector. And here's what we get. So hand in the Z, fingers curl into the X, thumb points in the positive Y. And I should point out that I've always gone from positives to positives here and gotten positive result vectors out, okay? Now, if we kind of look at this crudely, you can see that what I've been doing is I've been going counterclockwise sort of in this rotation. So as long as I go counterclockwise, I'm going to, if I'm using positive vectors and I go counterclockwise, then I'm going to get positive resultant vectors out that are perpendicular to the two other initial vectors. That's kind of what a right-handed coordinate system does. And the same thing is going to be true here with this particular system. And I'm not going to go through all of it, but I'll start with that last one that I did, which was Z to X. So if I go Z to X, then I get positive Y, just like before. It's just that the whole system has been rotated as a whole counterclockwise. I could rotate it as a whole clockwise, and I would still get the same result, as long as the orientation of everything follows the same sequence. Now, the sequence that needs to be is X to Y to Z to X to Y to Z, etc. Okay, so as long as you're going through that sequence, everything's going to work out fine. So X crossed with Y gives me Z, Y crossed with Z gives me X, Z crossed with X gives me Y. And these are all positives. So positive, 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 positive. As long as this is true, it's a right-hand coordinate system, I can use the right-hand rule. If, on the other hand, you go from, say, Z to Y, you will get a negative X. not a positive x, because you're going the wrong way. Okay, and I'll just do that real quick here. If I have z to y using this image, that's this right-hand rule, right? Up to the right, we get into the screen. So that's in the negative x direction. How did we get that? Using two initially positive vectors, positive z and positive y. We went the wrong way. We went backwards through our right-handed coordinate system. So this is also going to be really important as we get to more complex examples, where you have to understand that this is a sequential pattern going from XYZ, 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 etc. So that's all that I'm going to cover in this lecture. What we're going to do in the next one is look at a more complicated example, and maybe then even a more complicated example, just so that we visualize everything and hopefully fully understand the way that you can always get cross products right. And the way of doing that is to understand the coordinate system and the right-hand rule.